This is the video for Accelerated Geometry for Section 6-3 on Theoretical and Experimental Probability. As you can see that this section is loaded with vocabulary. We'll be talking about probability, outcome, sample space, event, equally likely outcomes, favorable outcomes, theoretical probability, the complement, an experiment, trial, and experimental probability. The essential question is, how do you find theoretical and experimental probability of an event? Probability is the measure of how likely an event is to occur. Each possible result of a probability experiment or situation is an outcome. The sample space is just a set of all possible outcomes, and an event is an outcome or in a set of outcomes. So for example, if we're talking about rolling a die or a number cube, there's 6 sides and numbered 1 through 6. So your sample space would literally be the numbers 1 through 6. If you're spinning a spinner with colors, then whatever those colors are would be in your sample space. So in this one, you have a red, a blue, a green, and a yellow section. Probabilities are written as fractions. Make sure that if you're going to write it as a fraction, that it is simplified. A decimal from 0 to 1, or as percent from 0% to 100%. So for example, you can leave your answer as 50%, 0.50, or as 1/2. Equally likely outcomes have the same chance of occurring. When you toss a fair coin, you get either heads or tails. So it's a 50% chance that you're going to have heads and a 50% chance you're going to have a tail. So these are considered equally likely outcomes. Favorable outcomes are outcomes of a specified event. For equally likely outcomes, the theoretical probability of an event is the ratio of the number of favorable outcomes to the total number of outcomes. So to put it as a formula for you, the probability of an event is just equal to the number of favorable outcomes divided by the number of outcomes in the sample space. Looking at some examples, it says each letter of the word probable is written on a separate card. The cards are placed face down and mixed up. What is the probability that a randomly selected card has a consonant? So if we look at the word, you can count the total number of letters. There's 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 possible outcomes. And what we're looking for is that it is a consonant. So we have 1, 2, 3, 4, 5 consonants. So the probability of getting what we want is just equal to the number of favorables, so the total number that there are, which is 5, out of the total possible, which is 8. And 5 over 8 can't be reduced any further, but we can write it as the decimal of 0.625, or we can leave it as 62.5%. It says 2 number cubes are rolled. What is the probability that the difference between the 2 numbers is 4? What I'm going to do is I'm going to pause the video in just a second after I get started here, and I suggest you write out your sample space for a problem like this so that you have something to look at. So if we're rolling 2 number cubes, that means on the first one you can get a 1, a 2, a 3, a 4, 5, or a 6. And on the second one you can get a 1, a 2, a 3, a 4, a 5, or a 6. So what possible combinations can I get? I can get a 1 and a 1. I can get a 1 and a 2. I can get a 1 and a 3, 1 and 4, 1 and 5, and 1 and 6. Or I can get a 2 and a 1, a 2 and a 2, a 2 and a 3, and I'm going to pause it and finish it. Okay, so our sample space is as follows, and if you count up the number of different sets of numbers that you have here, you will see that you have 36 possible outcomes. And the question wants to know the probability that the difference is 4. So if we look at our data here and find the sets where the difference is 4, you have a 5 and a 1, 6 and 2, a 1 and a 5, and a 2 and a 6. So there's 4 that are in my favor of getting out of the total 36. And 4 out of 36 reduces to 1 over 9, which is 0.111, which is 11.1%. You have a red number cube and a blue number cube that are rolled. If all the numbers are equally likely, what is the probability that the sum is 6? So again, I'm going to pause the video to draw out the sample space, and then as soon as I'm done, I would pause it yourself before I actually work the problem so that you could copy down the sample space. Okay, so here's our sample space, and I want to know what the probability that the sum is 6. So we can see that there's 36 possible. So we know our bottom number is going to be 36. And then if I look at these and find the ones that add to be 6, I can see I get it with a 1 and a 5, a 2 and a 4, a 3 and a 3, 4 and 2, 5 and 1. And so if I count them, there are 5 of them. And 5 out of 36 is 0.1388 or 13.88%. Example D says a red number cube and a blue number cube are rolled. If all the numbers are equally likely, what is the probability that the red cube is greater? So again, I'm going to go back to the sample space that I have before. I'm looking for the probability that the red cube is greater. And again, I know that there's 36 possible outcomes. So I'm going to look through these. On this first row, the red cube is never greater than the blue. The second row, you have the 2 is greater than the 1. Then you have 3 is greater than 1, 3 is greater than 2, 4 is greater than 1, 4 is greater than 2, 4 is greater than 3, the 5 and 1, 5 and 2, 5 and 3, 5 and 4, 6, 1, 6, 2, 6, 3, 6, 4, and 6, 5. So if I count these, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So 15 out of 36 reduces to 5 out of 12, which is 0.4166 or 41.66%. The sum of all probabilities in a sample space has to equal 1. The complement of an event E is the set of all outcomes in the sample space that are not in that event. So the probability of a complement of an event E is, so it's also written as the probability of not E, which the symbol for this is 2 different ways. The way you're going to see it in class is it could be written like this, that represents the complement, or you may also see it in another textbook on whoever writes another test, in AP Stat if you were to take it. They also may write it like this, which also stands for not E, not E, not E. All 3 of these mean the same thing. So the probability of a complement is just 1 minus the probability of that event. So if I don't want that event, then it's just 1 minus that event, because again, the sum of something happening and something not happening has to be 1. So let's look at some examples, so maybe this will make a little more sense to us. Okay, in example A, it says that there are 25 students in study hall. So this tells me the total number of students that I'm looking at. The table shows the number of students who are studying in foreign language. What is the probability of a random selected student is not, there's our key word, is not studying a foreign language? So first thing we're going to do is we're going to rewrite this using the complement notation. So I want to know the probability that somebody is not in foreign language, and again, I'm going to use the notation that you're going to see on worksheets in class. So we're going to say foreign language, and we want the complement of it. And that's just going to be 1 minus the probability that they are in foreign language. So we can find out the probability that they are in foreign language by looking at the chart. You have 6 plus 12 plus 21. This total is 21. So we have 21 students in foreign language out of the 25 total that they say are in the study hall. So the probability that they are in foreign language is 21 out of 25. So 1 minus 21 out of 25 would just be 4 out of 25, or 0.16, or 16%. Part B says 2 integers from 1 to 10 are randomly selected. The same number may be chosen twice. What is the probability that both numbers are less than 9? Okay, so you could sit here and draw out the sample spaces and look and see how many times it occurs, but that would take you a long time. So on a situation like this, using the complement makes it a whole lot easier. So the probability that a number is less than 9 would equal 1 minus the probability the complement of less than 9 would be greater than or equal to 9. So together, if you have numbers that are less than 9 and the numbers greater than or equal to 9, that would have your entire set of numbers. So if I look at the numbers, we have 1 minus. Between the numbers 1 and 10, the numbers that are greater than or equal to 9 would be 9 and 10. So that gives you 2 numbers out of the possible 10. So 1 minus 2 out of 10 would be 8 out of 10. Okay, so we are drawing 2 numbers. So the first number has an 8 out of 10 chance. The second number also has an 8 out of 10 chance because it says the same number may be chosen twice. And what we're going to do here is multiply. So if we multiply this, we would get 64 out of 100, which reduces to 16 out of 25, or 0.64, or 64%. Now, just kind of give you a heads up with this. As far as why did we multiply on this problem, that will be explained more when we do section 7-1. So the main thing that I wanted you to get from this example was this part over here with the fact that the complement of less than 9 was greater than or equal to 9. You can estimate the probability of an event by using data or by an experiment. For example, if a doctor states that an operation has an 80% probability of success, that means that 80% is an estimate of the probability based on similar case histories. Each repetition of an experiment is what we call a trial. The sample space of an experiment is the set of all possible outcomes. The experimental probability of an event is the ratio of the number of times that the event occurs, which is also called the frequency, to the number of trials. So we have the number of times it actually happened over the total number of trials that were in the experiment. Experimental probability is often used to estimate theoretical probability and to make predictions. So our first example here, we're looking at a spinner experiment, and we are wanting to know what is the experimental probability of spinning a 4. So what I'm going to do first is I'm going to add 6, 11, 19, and 14, because that will give me my total. So if I do that, I will get 50. So spinning a 4, so the probability of getting a 4, according to this experiment, happened 14 times out of the 50 trials that happen. So if I reduce that fraction, I will get 7 out of 25, or I will get 0.28, or 28%. What about spinning a number greater than 2? So I'm going to look at my table here, and I have two options here that are greater than 2. I can get a 3 or a 4. So I have 19 and 14. So the probability of getting a number greater than 2, I'm going to take the 19 and add the 14 out of the total 50. So 19 and 14 give me 33. And 33 out of 50 is 0.66, or 66%. Let's try two more. Now we're looking at the results of choosing one card from a deck and recording their suits and then replacing the card. So it says, find the experimental probability of choosing a diamond. So the probability that I get a diamond is equal to, again, the first thing I'm going to do here is find my total. So 5 plus 9 plus 7 plus 5 is going to give me 26. So I have 9 diamonds out of the 26 trials, and 9 out of 26 is 0.346, or 34.6%. Find the experimental probability of choosing a card that is not a club. So the probability of not a club, which is a complement, would be 1 minus the probability that it is a club. So that's going to give me 1 minus, if we look at our chart, a club happened 7 times out of the 26. So 1 minus 7 out of 26 would be 19 out of 26, which is 0.731, or 73.1%.